So we were looking at this, and the notion of consistency. We said that this set of formulas is consistent if it cannot prove a statement and its negation, or if there is anything that it cannot prove. So we had the notion of consistency, and we had this theorem that says that any consistent set of WAFs sigma can be extended to sigma prime, which is a superset of sigma that is maximally consistent. Now this result is, of course, very similar to a similar result we had with respect to satisfiability. We proved it for satisfiability that every satisfiable set of formulas can be extended to a maximally satisfiable set of formulas, but that was in the context of semantics, and this is in the context of syntax. You look at me as if I'm saying something odd or weird or, okay. Okay, so now what did we do with the proof? The proof was very similar in structure to the proof that you saw for the case of satisfiability. So what is the proof idea? The proof is we construct a sequence of sets of WAFs sigma 0, subset of sigma 1, and so on, subset of sigma I, which is subset of sigma I plus 1 for all I, such that we satisfy the following requirements. So the first requirement is very simple. Our sigma 0 is the sigma that was given to us. And the second requirement is that for all I, sigma I is consistent. And the third requirement is really the crucial one, and it says that for some fixed enumeration of all WAFs, so I have an enumeration alpha 1, alpha 2, alpha n, that enumerates all WAFs. And in order to get such enumeration, I have to restrict my set of variables. So say over the variables p1, p2, pn, and so on. So I have only countably many variables. Then I can list a set of all WAFs. And for such an enumeration, what I want is that for all I, either sigma I proves alpha I, or sigma I proves the negation of alpha I. So we construct this sequence. And what we did last time is that I showed you that this can be constructed. I gave you an inductive definition of the construction, what to do at stage I plus 1, assuming you have already managed to get to sigma I. So the construction was just based on that. So sure, for sigma 0, we know how to start. And to define, assuming sigma I is defined and meets the requirements, let sigma I plus 1 be sigma I if sigma I can prove alpha I plus 1, the negation of alpha I plus 1, and sigma I union alpha I plus 1 otherwise. So when we get to decide on how to extend sigma I to sigma I plus 1, we pick the next alpha in the list of formulas, the next formula that we haven't decided yet. And we check. If sigma I already made a decision about it, it proved that it should not edit its negation, then we don't have to do anything. If sigma I did not prove its negation, then I add alpha I plus 1. So what happens if sigma I proved alpha I plus 1? What? If sigma I already, if it proves not alpha I plus 1, we are here. What happens if it did prove sigma I plus 1? Then I'm in this case, and I'll add alpha I plus 1 here. It wouldn't hurt me, because if it already proved it and I add it, at the worst case, I didn't do anything. So last time, all we need to prove here, if we can carry out this construction, we clearly meet all the requirements. The only thing that we need to prove is that under, so we have here the claim that under, assuming sigma I meets the requirements then, so will sigma I plus 1 defined above. So we want to make sure that our definition pushes forward to sigma I plus 1, meeting the requirements. So requirement 1 is irrelevant. We only care about it at the first step. Requirement 2 is the crucial one. Requirement 3 is obvious, because sigma I plus 1, when we get to alpha I plus 1, either we already had it, we already prove its negation, or we add it and now we can prove alpha I plus 1. So the only thing we have to worry about is consistency. And I think I did it last time, right? Or you don't know? Yes?
I think you did it under a claim that if sigma union alpha proves not alpha, then sigma proves not alpha.
Right. So we did it under the claim that, the worry was that this will become inconsistent. Right? If this becomes inconsistent, it means that this can prove not alpha I plus 1. But what we claimed is that if using alpha I plus 1 we can prove not alpha I plus 1, we could have proved it before. And in that case, we would not have changed sigma I. Right? So the claim that we need a kind of a side claim. That's all we need for the consistency. And it says that for every sigma and alpha, if sigma union alpha proves not alpha, then sigma doesn't need alpha to prove not alpha. You see, this would sort out our concern that this may become inconsistent. Because if it becomes inconsistent, it can prove everything. In particular, it can prove not alpha. But if using alpha I could prove not alpha, then the lemma tells me that sigma alone can prove not alpha. But that will bring me to the first case, in which case I didn't change sigma. Right? So if I kill the consistency, then it is the case that I would not have changed sigma, so the consistency was bad before, which violates our assumption that sigma I was consistent. Now, to show the claim, I will only reduce it to a statement about formal proofs. I mean, here we need a formal proof. But what we need for here, so to show the claim, to prove the subclaim, it suffices to show that we can prove from our proof system that if alpha arrows not alpha, then not alpha. So this is something, for this we need a formal proof. And I don't want to go back now to doing formal proofs. I will put it in the next assignment with guidance, the formal proof that we're missing here. But what I'm saying is that if we had this proof, then everything would be okay. Why this will be okay? I mean, why will this suffice? Because, okay, so now why does it suffice? Right? So assume sigma union alpha proves not alpha. Then, and now I'm asking you, by what? Sigma proves that alpha arrows not alpha. Yes?
1 or 2, 3.
No.
Deduction.
It's deduction. It's deduction theorem. See, because what I did is I took the alpha from here and moved it into the head of the arrow. You see what happened here? I had alpha as an assumption, and now I got it out of the assumptions, and I have only sigma here, and I have it at the head of the arrow. So this is deduction theorem. We have this. Now, if I know this guy, if this can be proven from without assumptions, I can write it here, alpha arrows not alpha, arrows alpha, arrows not alpha, and do modus ponens, and get not alpha. So I got a proof from sigma of not alpha. See, this is what I wanted. So based on this, if we can prove this statement, the formal statement there, we get the side claim. Again, the side claim was if sigma needed the enforcement of alpha to help it prove not alpha, then I can tell sigma, don't worry, you could have done it on your own. You could have proved not alpha without this help. Because this help is going in the wrong direction. It cannot be useful. That's the intuition behind this claim. The formality is that from here you use the deduction theorem to say in that case you will have this. And then you will use this formal statement there to get a proof of not alpha by modus ponens. Okay, so now the logic here is a little bit kind of, we are doing a lot of rounds. So why did we need this side claim? Because this side claim guarantees that sigma I plus 1 is consistent. So now the corollary our construction of sigma i's can be carried out while respecting or observing, whatever, what you want to say, respecting, okay. Respecting requirements 1, 2, 3. What we do our construction, we go to the next step and construct sigma I plus 1. It is not going to be inconsistent. So yeah, it's a little bit confusing because the logical structure here is we wanted to prove that sigma consistent is a subset of sigma prime, which is maximum consistent. For this, to get this, we wanted to construct this sequence, sigma I, subset sigma I plus 1. To do this, we needed to show that sigma I plus 1 is consistent. To do this, we needed the subclaim. And to prove the subclaim, we needed this statement that alpha errors not alpha, errors not alpha. So there's a long chain of reasoning here. And this is the only step that I didn't show, because this needs a formal proof. So this is where we are. So we are now here. We climbed up and we got to this point. We know how to construct the sequence. We haven't yet shown that we can get a maximally consistent sigma prime. Okay, are you with me, or do you have questions? Or so if anybody has a reasonably organized set of notes, I'll appreciate getting a copy of that. Okay? Because as you see, I'm lecturing kind of out of thin air, so it's nice to have it written down. Okay, so let's finish our claim. We want to get a sigma prime that is going to be maximally consistent. So now, how do we get sigma prime? So we were given sigma, we constructed this sequence, sigma subset of sigma 1, subset of sigma I, subset of sigma I plus 1, and it went on for every I. Now, define sigma prime to be the union over all natural numbers of sigma I. So sigma prime is going to be the union of all of those sets. It's an infinite union. We have sigmas that keep growing, and then we take the union. So it's not any of those, because each of them is bigger and bigger and bigger. Yes?
So technically, isn't that just the last sigma?
That's exactly what I wanted to express. Right. Why isn't it just the last sigma? That's really the most confusing question. We need to address it. Why isn't it just the last sigma? Because there is no last. Because for every sigma I, we build sigma I plus 1. For every sigma I, we build sigma I plus 1. So there's no last. So this is a bit confusing, because we usually, if you have sets that are ordered by inclusion and you take the union, it's just the largest of them. But there's infinitely many of them. It's just that, think of it as this example. Think that your A A0 is just 0, and A1 is 0, 1, and AN is 0, 1, 2, up to n, and so on. So we have this property that AN is a subset of AN plus 1, and so on. Right? What is the union of all of those AIs? It's all of the natural numbers, right? Each AI contains more and more and more and more and more natural numbers. So the union is all of the natural numbers. But each individual set is finite. So the union is much bigger than any of the individual sets in the sequence. So each individual set here is just a finite set. But the union becomes suddenly infinite. So the union can be very different than each of the sets in the sequence. Okay, so thank you for this question, because I think this is one of the points that, I mean, from my point of view, doing it over and over again, I don't bother to even mention it. From the point of view of a student, this is a pitfall where you can get confused. Okay, so we have this sigma prime. What we want to prove is that sigma prime is maximally consistent. And notice that this is not absolutely, I mean, it's not a trivial statement. So we have a claim that the sigma prime we constructed is maximally consistent. So we need to show two things. We need to show that it's consistent, and we need to show that it satisfies the maximality requirement. The maximality requirement is kind of easy. So the proof consists of two parts. The maximality is easy, so I'll start with this. For every alpha, I want to show that either this sigma prime proves alpha or sigma prime proves neg alpha. So what happens? For every alpha, it appears in the list. Alpha equals alpha I for some I in n. Because our sequence alpha i's listed all of the possible formulas. So if you come up with some formula, it will be one of my alpha i's. Therefore, by requirement 2, sigma I proves alpha I, or sigma I proves the negation of alpha I. So, in other words, sigma I proves alpha, or sigma I proves the negation of alpha. So we started with some alpha. We got to some sigma I that either proved alpha, either proved the negation of alpha. Right? Now, why? I don't care about sigma I care about sigma prime. So why does sigma prime prove either alpha or not alpha?
Sigma I is a sigma prime subset.
Right. Now, each sigma I is a subset of sigma prime, because sigma prime is the union of all of the sigma i's. So each of the particular sigma I is a subset. Therefore, by which property now I get that sigma proves alpha or sigma proves not alpha? By which property? Now it is monotonicity, right? So by monotonicity, sigma prime proves alpha, or sigma prime proves not alpha. So we are done with maximality. We still have to worry about consistency. So now we have this claim, sigma prime is also consistent. And that's a little bit less obvious. It's not hard, but it's a bit less obvious. And this relies on an interesting property of our proof system. Our proof system is such that every proof is finite. So assume by way of contradiction, it is not. In that case, for some, let's call it alpha, sigma prime proves alpha, and sigma prime proves neg alpha. Now I'm going to use the fact that every proof is finite. So let, say, beta 1 up to some beta k be a formal proof of alpha from sigma prime, and let, say, gamma 1 up to gamma k prime a formal proof of neg alpha from sigma prime, because if it is inconsistent, it can prove both alpha and neg alpha. So now what we are going to do is we are going to say how is sigma prime constructed? It's constructed by an increasing union. So we have here sigma 0, subset sigma 1, sigma I plus 1. And the union of all of this, we take the union of all of this, and we get sigma. So for each of those proofs, we can check what is a proof. A proof is a sequence such that every element here is either an axiom or an assumption, or it follows from previous guys by modus ponens, right? So what I care about is the assumptions. So I'll collect all the assumptions from both of these proofs. So each beta I that is an assumption from sigma prime in that proof belongs to some sigma, call it mi. So I look at the proof, and each time it comes, the proof uses an assumption, I look at this assumption and ask, sure, the assumption comes from this big union. If it comes from the big union, it came from one of the components. So this beta I resided in some element here. I call this element sigma mi. I mean, it's not, I don't know what is the index, so I'll call it mi. And similarly, each gamma j, say, that is an assumption, belongs to some sigma mj. Now, there are finitely many of those. So, since both formal proofs of alpha and of neg alpha are finite, there is some I star that is bigger than all of these MIs, and MJs. So I can find someone here. I can find here some sigma I star that is far enough in the sequence that all the assumptions that I used occurred before I got to the level I star. So for each, therefore, for each beta I or gamma j that are used as assumptions, in these proofs, this beta I, gamma j are members of sigma I star. Because I went far enough in the sequence to have a big enough set that captures everything I used in the proofs. Now I want to get a contradiction. How do I get a contradiction now?
Sigma I star is
Right. So by monotonicity, now by monotonicity, I don't even need monotonicity, this sigma I star can prove alpha, and sigma I star can prove neg alpha, because it contains all the assumptions that I needed in order to carry out both of those proofs. So the sigma I star, it contains all the assumptions that were used. So sigma I star is inconsistent. So sigma I star is inconsistent. And that's contradicting requirement 2 in our construction. Because in our construction, requirement 2 said each alpha I is consistent. So we showed that if sigma prime is inconsistent, then one of the sigma i's would have been inconsistent, which is a contradiction. So we finished the proof of this. We arrived here. Every consistent sigma can be extended to a maximally consistent sigma prime. Now, I want to use it to get one more link in our table. So we had this table of syntax and semantics. You remember we had this table that will go with us throughout the course of syntax versus semantics. And here we have the notion of sigma being consistent and sigma being maximally consistent. And here we have the notion of sigma being satisfiable and sigma being maximally satisfiable. And we've already seen that if it is satisfiable, then it is consistent. This we've already seen. Now I want to show you this direction. That if it is consistent, then it is satisfiable. And then we will also show equivalence between these two. So I have a nice syntax semantics theorem. Every consistent sigma is satisfiable. Now, initially, it looks like something which hard to attack. I know that it's consistent. What do I know? I know that it cannot prove a contradiction, right? Now, to show it's satisfiable, I should come up with a truth assignment. Where am I going to get my truth assignment from? I mean, all I know is that this guy, this sigma, is not too strong. It cannot prove a contradiction. Very nice, he's weak. Now, how do I find a assignment, truth assignment for it? So here is a nice trick. So the proof, we start with the last theorem. So let sigma prime be a maximal consistent set of WAFs such that sigma is a subset of sigma prime. Now, why will it help me? Now I'm going to define a truth assignment. Because in order to show satisfiability, I need to define a truth assignment. So define a truth assignment V of sigma prime as follows. For every pi, I have to tell you whether it is going to get value true or false. So V sigma prime of pi is going to be true if sigma prime proves pi and false otherwise. So I need to define a truth assignment. You give me a variable pi, but the variable is also a formula. So I can check if sigma prime can prove it or not. If it can prove it, I'll give it true. If it cannot prove it, I'll give it false. So that's a well-defined truth assignment. This is well-defined no matter what I put here. For every sigma, it's a well-defined truth assignment. And now, the claim that we get is kind of completes our cycle of reasoning. So now we have a claim for every formula alpha, V sigma prime of alpha equals T if and only if sigma prime can prove alpha. So what I started with doing it for propositional variables. For propositional variables, I defined it. It is defined as true if and only if I can prove it. But now I claim that this is going to happen for every alpha. Okay? And if we do this, we get satisfiability because it's sigma prime now. Every formula of sigma, sigma prime can prove it. So every formula of sigma will get true. So it will turn out that this V is a satisfying assignment for sigma. So this will establish the theorem, but in order to show this claim, I need more time. So this is pushed to next Tuesday. Okay, so lecture at Humanities Hall in 13 minutes. See you there. Thank you.